So here is the final exam prep for the part of the exam that concerns topics of test 2 and test 3. We'll start by the Bernoulli equations. So a Bernoulli equation is an equation of the type dy over dx plus p of x y equals f of x times y to the power n. So it's just a linear first order differential equations for which we just multiply the right hand side by y to the power n. An example here would be x dy over dx minus 2y equals x squared minus 1 over x. Let's say we have such a thing as a function, as equation multiplied by y cubed, or let's say here y squared. So that's the equation. This form is called the standard form of the equation. It's clear that this example is not given in the standard form. So anytime you have such an equation, the first thing to do is bring it to the standard form. So bring the equation to the standard form. You do that by dividing the entire equation by the coefficient of the first derivative. So in this case, we will have dy over dx minus 2 over x y equals, and when you divide this by x, you get x minus 1 over x squared times y squared. The next thing to do is divide the equation. So divide the entire equation by y to the power n and set w equals y to the power 1 minus n and find dw over dx equals 1 minus n y to the power negative n dy over dx. So this derivative is obtained using the chain rule. Because y is a function of x, you want to take the derivative of this thing with respect to x. You take derivative as if it was just y, and then you multiply by the derivative of y with respect to x, which is dy over dx. And so here we have 1 over y to the n dy over dx. That's what we get when we divide by y to the n. In this problem, it's going to be 1 over y squared plus, and here it's minus 2 over x times y to the power 1 minus 2 minus 1 equals x minus 1 over x squared. So when we set this thing here equal y to the power 1 minus n, in our example, that is y to the power 1 minus 2, which is y to the minus 1. So this is that w that we just set there. And here, our dw over dx in our example with n equals 2 is negative y2 minus 2 dy over dx. And so here, if you look carefully, you would see that this piece here is exactly what we have here. The difference is that you got a negative sign in front. So we put that in here. In the next step, substitute w and dw over dx. So we substitute them in the equation, and we are going to have negative because we have this minus here. 1 over y squared dy over dx, that's negative dw over dx. So we get negative dw over dx minus 2 over x, and this is w equals x minus 1 over x squared. Anytime you do the substitution, what you are going to obtain is a first order linear ODE. That's it. So you solve this using what we do for first order linear ODEs. So you can assume this is a second example of linear ODE that you're solving from here on. So the first thing to do again is bring it to the standard form. So bring the equation to the standard form, and the standard form for linear differential equations is dw over dx plus p of x w equals f of x. So here that means divide the whole equation by anything that is in front of dw over dx. In this case, it's minus 1. So when we do this, we get dw over dx plus 2 over xw equals x minus plus 1 over x squared. So this is what we obtain, linear equation in the standard form. And to solve that equation, the first step is find mu of x, the integrating factor, which is e to the integral of p of x dx. P of x in this case is right there, including the sign. If that was a minus, that would include the sign. So here, it's e to the integral of 2 over x dx, which is e to the 2 natural log of x. And that's e to the natural log of x squared. That is x squared. So the integrating factor in this case is x squared. And the next thing is therefore multiply the whole equation. Multiply this equation by the integrating factor. In this case, we obtain x squared times this whole thing, so that's x squared dw over dx plus 2xw equals multiplied by x squared, that's negative x cubed plus 1. So this is what you get when you multiply both sides of the equation by the integrating factor. The next thing to do is combine terms on the left as d over dx of the integrating factor times w. In this case, in our example, that is d over dx. In any case, it's always going to be that. And if you do check here, you see the derivative of x squared is 2x. So that's why this thing here is derivative of x squared w, which is derivative of the integrating factor times w, equals, and the right hand side is what it is, minus x cubed plus 1. And the next step is integrate both sides. So when you integrate the left, you get x squared w. You integrate the right, you get negative x to the fourth over 4 plus x plus a constant of integration. And the next thing to do now is to return w equals y to the 1 minus n. In this case, it's y to negative 1, so 1 over y, so you get x squared over y equal negative x to the fourth over 4 plus x plus c, that we can solve for y. You get 1 over y equals negative x squared over 4 plus 1 over x plus c over x squared. Make sure you don't get any mistakes at this point with the algebra. You can keep your final answer at this point. That's it. That's how you solve the Bernoulli equation. The next question would be reduction of order. So how do we answer questions for reduction of order? And the question would be clearly, use the reduction of order to solve the following problem. An example is going to be use reduction of order to solve one plus x times y double prime plus x y prime minus y equals 0, given that y1 equals x is a solution. So that's the setup of the question. So you know one solution, and you want to find the general solution to the problem. The equation, in this case, is 1 plus x y double prime plus xy prime minus y equals 0. So how do we answer the question? Here are the steps. The first step is bring the equation to standard form. Bring the equation to the standard form. And the standard form is y double prime plus p of x y prime plus q of x y equals 0. Once you do that, you continue solving the problem by finding the Wronskian. is a constant times e to the negative integral of p of x dx. This uses Abel's theorem. Finding that, just like compute this integral. So that is c e to the, in our example, when we bring it to the standard form, we get y double prime plus x over x plus 1, y prime minus y over x plus 1 equals 0. So p of x is this. That's p of x. So that's e to the negative integral of x over x plus 1 dx. And this is c e to the negative integral of x plus 1 minus 1 over x plus 1 dx. So c e to the negative integral of 1 minus 1 over x plus 1 dx. Computing that integral, I get c e to negative x, integral of 1 is x, and integral of dx over x plus 1 is natural log of x plus 1. So that is c e to negative x times e to natural log of x plus 1, which is nothing but c x plus 1 e to negative x. Why is that? Because e to natural log of x plus 1 is x plus 1. So this is what the Wronskian is equal to using Abel's theorem. And then you write the Wronskian separately on the other side. The Wronskian is equal to v prime y1 squared, where y that you're looking for is equal to v y1. In this case, it is v and y1 is x. So we get that w equals v prime and y1 squared is x squared. But at the same time, that w is what we got here. So that's c x plus 1 e to negative x. And from that, you can solve and find v prime equals c x plus 1 over x squared e to negative x. And therefore you get to that last step and you integrate to find v. And you integrate this. And then you can write y over x equals v of x times y1 of x.